chapter to complete. This is chapter 5 of groups. Now this is quite different to the material we've been doing up to now, the kind of calculus type material about convergence and differentiation and integrations. This is an example of what roughly falls in, sometimes people call this the area of discrete mathematics. But groups are very important family of objects that appear in many places in mathematics. And there's a whole third-year course on them called group theory, where we study these things in extreme detail and build up a lot of the theory about them. And so they're important. They're considered important because they're present in a lot of mathematical areas, a lot of mathematical structures that we look at. And they have a very rich and interesting structure themselves. And there's lots of interesting pure mathematics problems within the realm of group theory itself. So what is a group? Well, you're already quite familiar with several examples of groups, although you may not have encountered the term group before. So a group, so we see here in the first definition, and we'll explore some examples in a moment. This is just the definition. So a group is a pair of objects. It's a G and a star. So normally read that asterisk symbol as star. So G is a set of objects, some kind of a set of some kind of mathematical objects. And star is what is called a binary operation on the set of objects. Now you're already intimately familiar with several binary operations. A binary operation is a kind of an operation where you take two elements, you apply the binary operation to them, and it produces a third element. Okay? So addition of numbers is a binary operation. You take two numbers, you add them together, you get a value, a third number. Multiplication of numbers. Okay? Addition of functions, multiplication of real valued functions. Those are binary operations on functions. You know at least two binary operations that can be performed on matrices, sets of matrices of certain sizes. If you have matrices of the same order, the same dimension, you can add them together. Addition of matrices is a binary operation. It's a rule, it's an operation that takes two matrices, combines them together in some mathematically meaningful way, and gives you a value matrix, a third matrix. In the same way, if you have two matrices whose dimensions are compatible, or if they're two square matrices of the same size, you can multiply them. It's a very meaningful operation. It corresponds to the composition of the linear transformation represented by those matrices. But that again is an example of a binary operation, taking two objects and combining them together to give a third same type of object. So this is the situation that group theory studies. Okay? Anywhere where you've got a set, mathematical objects, and a binary operation. Okay? But it's not any old set. There's a minimal set of conditions that the pair, the set and the operation, have to satisfy in order to be called a group. Okay? We don't just accept any set in any binary operation. It has to qualify. It has to satisfy this number of conditions in order to be called a group. Okay. So we'll go through these conditions here. So we're still talking in abstract. We're not talking about any specific groups here. Just showing the definition for a group. Then we'll look at some examples. And so the first axiom is called a closure axiom, and that says that whenever you take two elements A and B and G, the value of the binary operation on A and B, A star B, that is always an element of the same set. Okay? We refer to that property as saying that the set is closed under the operation. Okay? You take two elements from the set, perform the operation with them, the value you get is present in that set, not outside of the set. Okay? It is present in the set G. And that has to be true for every pair of elements that you take and you perform the binary operation. Secondly, the operation has to be associative. Now, associativity, which I think you probably encountered when in the linear algebra when you're discussing matrix operations, Associativity says, well, if you want to take three elements, an A, B, and C, and combine them with the operation so that A is to the left of B and B is to the left of C. Well, you see, the binary operation is a rule for combining pairs of elements, ordered pairs of elements, the first one and the second. So a triple product can be interpreted in two different ways. You can either think of it, like shown on the left here, that first you take the operation of B star C, and then with the value of that, you do A star, whatever the value of that is. Or you could interpret it, you could evaluate it the other way. You could first take the product A star B, sometimes referred to these as products in general. The product of A and B, A star B, and then take the product of that value with C. Those are two different ways to evaluate the triple product. The operation is associative on the set, but those two ways always give the same value. Okay? So when it doesn't matter what way you bracket up a triple product like that. The third property is the existence of an identity. So an identity element is a special element. It's traditionally denoted E after the word eigen in German. A lot of the group theory terms come from German. So E for eigen, which is kind of singular or oneness kind of notion. There's a special element E called the identity, and it is the special property that when you take the product of it with any other element A, it leaves the other element unchanged. The value you get back is always exactly A. Okay. So there exists some special element in the set such that for every A in the set G, E times A, product of E and A is equal to the product of A and E, and that's equal to A. The fourth condition is the existence of inverses. And that says every element in the set A, whatever element A you look at, there will exist another element. In this kind of notational setup, it's denoted A superscript -1, and it's read in English as A inverse. And there exists a special element A inverse in G, and that has the property that when you take the product of A with A inverse in either order, you get back the special element E, the identity element, which was mentioned in the previous sentence. If the system, by the system I mean the set G together with the operation, if the system satisfies those four axioms, then it's called a group. So you can kind of think of these conditions as, in some way, the kind of minimal set of conditions we require in order to call the thing kind of mathematically interesting in some kind of way. So just a few remarks there following the definition. Note, strictly speaking, so sometimes we slip into the language of referring to the group G. But strictly speaking, the group is the pair of things, the set G together with the operation. Because there are situations where there are multiple operations, multiple different operations you can define on a set that give rise to different group structures. Okay? So the group is the pair of things. But in practice, as it says here, in practice as you go along, as long as it's clearly understood what the operation you're referring to is, we often slip into this language of referring to the group G. But strictly speaking, it's the group together with the operation. It's a pair of things. And finally, just to note that in general, so this condition here is called commutativity. If it's always the case that for every A and B, the product of A with B is the same as the product of B with A, then the operation is called commutative. Okay? Now that's not part of the definition of the group. Okay, but that's kind of the first broad classification of groups. Some groups are, we refer to the operation as being commutative, but we refer to the group as being abelian. That's named after Abel, Norwegian mathematician, I think. So the group is called abelian if the operation is commutative on the group, and it's non-abelian if it isn't. So that's the first kind of broad classification of groups. Some groups are abelian, some groups aren't. Now, what's your favorite non-commutative operation? I'm tempted to pick someone at random, but somebody volunteer. What's your favorite non-commutative operation? Or just what's one that you've encountered recently? You've encountered a few of them in at least one in this unit and at least one in another unit. Non-commutative operation. So which collection of mathematical objects and which operation on them was not commutative? Okay, so the set of matrices and for which operation? Multiplication of matrices. You've got two square matrices of the same size, you can multiply them, and you can multiply them in either order. You can put A on the left and B on the right, or you can put it the other way around, B on the left and A on the right. And in general, the two product matrices will not be the same. Okay, good. Sometimes they are the same if the matrices have special properties, but in general, you shouldn't expect a matrix product to be the same when you change the order of the factors in it. Okay. What was the important operation we met in this unit specifically that we emphasized wasn't commutative? And this one is very important for group theory. It's kind of related to that example of multiplication matrices. That was the operation of composition of functions, okay? Composing functions together. You do one function f first, say real value function that gives you value, and then apply another function g to the value of that. In general, you'll get different results if you apply the functions in the opposite order. You first apply g, and then after that apply f. And that's a universal rule just about reality. It typically makes a difference the order in which you combine actions. My funny example was, how sad I am repeating my jokes, but there's two operations involved in making a cake. The first operation is mixing the ingredients, flour and water and sugar, whatever. Mix the ingredients, that's the first operation. The second, you get a mixture. The second operation is to cook the mixture. You do it that way, you get a lovely cake at the end. But if you reverse the order of the operations, if you first cook the ingredients separately, cook the butter, it melts. Cook the flour, it just kind of hardens into a lump of dry flour. Cook the water, it might reduce a bit. Cook the sugar, it might go into sticky syrup. And then mix it, you don't get a cake, you just get a mess of semi-burnt ingredients. Yeah? So if you think about combining operations, most of the time it makes a difference the order in which you combine them. So things are by no means always commutative. In fact, it's rare to find commutative things. We're kind of lulled into thinking that most things are commutative because of the arithmetic operations on numbers. Adding numbers, multiplying numbers. Okay, those are commutative. But the very other important operation, composing functions, that's not commutative. And the reason I linked it with the multiplication of matrices is multiplication of matrices is, in effect, composition of functions. Because the matrices represent linear transformations. Have you talked about linear transformations in linear algebra? Yeah, these functions from vector spaces to other vector spaces. So matrices represent linear transformations, and multiplying the matrices, it represents composing the linear transformations. Okay. And in group theory, groups that are abelian, or the operation is commutative, are pretty well understood. They're kind of easy to understand in some ways. Because the fact that the operation always commutes like that means you can understand the structures in the groups fairly readily. However, the difficulty arises is that there's, most of the important kinds of groups are not commutative, and that makes the situation a lot harder. It kind of sounds negative, but in the other flip side of that, it means there's a lot richer structure to find there. Non-abelian groups have a lot more going on with them. They're more sophisticated. They've got more structure. They're harder to understand and get a grip of, but then that makes them mathematically interesting. Okay. So that's the definition of what a group is. So we should immediately go through a collection of examples. Because it's one thing to think kind of in abstract terms about what a group might be, but you want to be pretty sure that they exist and that there's enough of them to warrant to warrant a separate investigation. So probably the most readily available example to you, and this is something that primary school children would recognize. This is the integers under addition. So the set is the set of integers. Hope everybody's clear on what the integers are. So the counting numbers and their negatives and 0. And the operation is just plain old addition. So does this satisfy the conditions in the definition? Now, we're not going to give a proof so much, like a proving that the conditions are satisfied for the integers. That would involve some kind of quite dry technical set theory work based on what exactly the integers are. And even though you might think the integers are kind of very primal and God-given in some ways, you can construct them out of even more basic concepts using set theory. But let's just take the integers as being out there and readily graspable by us. We'll just kind of illustrate that the conditions are satisfied. Just kind of reassure ourselves that the conditions are satisfied. So first of all, closure. If I've got two integers, z1 and z2, is z1 plus z2 always an integer? Question mark. Take two integers, minus 17 plus 23, add them together. Yeah, you're going to get another integer. Okay? Nothing can go wrong to suddenly produce a fraction or suddenly produce a real number or suddenly produce a matrix when you add two integers. So that counts. Okay? So you take two integers and add them. Yes, you do always get another integer. Associativity. Associativity. We want to spell that quickly. If you take z1, z2, and z3, is z1 plus z2 plus z3, is that always the same as z1 plus z2 plus z3? Question mark. If you go out for a walk and, first you walk 2 miles and then you walk 3 miles and then you walk 5 miles, is that the same as first walking 5 miles and 2 miles and then walking 3 miles? Yeah. Both sides is just the accumulation, the sum of all three quantities. It doesn't make a difference. E.g., you add minus 6 plus 2 plus 7. Is that the same as minus 6 plus 2 plus 7? Yeah, it is. This is by no means a proof of it, but we're just kind of confirming that this is some familiar feature of the integers that we're familiar with. So what you get here, minus 4 plus 7, so it's 3. Minus 6 plus 9, yeah, it's 3. It's not a proof, but we're just reminding ourselves, reassuring ourselves. Okay, axiom 3 says there exists a special element called the identity. What is it? Huh? 0 is the identity. Excellent. Okay. Right, because if you take any integer x, if x is any integer, and you add 0 to it, that's always going to be the same as adding 0 to x, and it's always just going to leave you with x. Okay? That's exactly the property that the identity is supposed to have. So yes. Does every integer have an inverse? Yes, the inverse of x is minus x. Okay. Why? Since if you take your x and you add it to your minus x, okay, the property that the inverse element is supposed to have is that when you perform the operation between it and its partner, you're supposed to get back the identity element. And that's a familiar fact to us about addition of integers. If you add x with minus x, they cancel, sometimes we say, and we get 0. Okay, note here we don't use the superscript -1 notation. Superscript -1 notation is kind of multiplicative notation. But we wouldn't use multiplicative notation to talk about the operation, an addition-like operation. So here the inverses are denoted as negatives. So all this all seems fine. All seems fine. So the integers under addition is a group. It's not a proof of this would really require examining the set theoretic construction of the integers out of something more basic and a kind of really careful examination of what this operation addition is. But I think at this level, we're happy to just kind of confirm it by recognizing the conditions in the context of the integers. Is it abelian or non-abelian though? Is the operation commutative or non-commutative? It's commutative, okay? It's abelian for, if you take any pair of integers x and y, it's always the case that x plus y is equal to y plus x. Okay? Both of them are just the sum of the two quantities. Okay, what about the integers under multiplication? Does that form a group? Do the integers under multiplication form a group? So to answer that question, you have to run through the axioms and run through the conditions. Sometimes people call them the group axioms, but group axioms for a group or conditions for the definition of a group, referring to the same thing. So if you look at those parts of the definition on your page, do the integers under multiplication satisfy each of them? Or is there a problem? You can probably guess by the way I'm posing that question, there is a problem. So what is the problem with the integers under multiplication? Anybody?
Identity?
Yeah, so is there an identity for multiplication?
Well, if it's 0, if you multiply by 0, you get 0 instead of 8.
Yeah. So 0 isn't the identity. So the identity element is a special element such that when you multiply it by any integer, it leaves the other integer unchanged.
Yeah, 1.
1. So there is an identity element. So the problem isn't in axiom 3, condition 3. So there is an identity. 1 is the identity of multiplication.
The inverse.
The inverse. So for a specific example,
Like 3. 1 over 3.
3. Yeah. So closure is fine. Multiply two integers, you get an integer. Associativity is fine. Multiplication of integers is associative. Identity is fine. It's 1. But the problem is inverses. Hardly anything has an inverse. 3 does not have an inverse. Okay, well you say, well, it does have an inverse at the third, but the point is a third is not present in the set we're talking about. Okay? So 3, and in fact any Well, there's three special integers that do have inverses. What are they? Okay, one, did you say one?
Yeah.
So one has an inverse, which is itself, one. Sorry, there's only two that have inverses. What's the other one that has an inverse? Minus one. It is its own inverse as well. There's nothing in the inverse axiom that says the inverse has to be a separate element. Something can be its own inverse. But except for 1 and minus 1, nothing else has an inverse. So it doesn't look good for the integers under multiplication. But there are multiplicative number groups. What about the real numbers under multiplication? This will get around the problem of a third not being in the integers. Because the real numbers do contain the reciprocals of all their elements. Of course, closure is going to be fine. You multiply two real numbers, you get a real number. Associativity is fine. Multiplication of numbers is associative. Existence of identity is fine. The identity is 1. And inverses looks okay. You just have to be very careful that there's still a problem with the inverses axiom. Okay, most things have inverses here. For like 3, the inverse is 1 over 3. And for any integer y, the inverse is going to be 1 over y. And that's fine except for
0.
0. Yeah. You can't say the inverse of 0 is 1 over 0 because 1 over 0, well, you either say it's undefined or you might say it's infinity or something, but infinity is certainly not real. So it's all fine except no inverse for 0. So there's an easy way to fix that. You just throw 0 out the door. So the group, there is a group, a multiplicative group of real numbers, as long as you just exclude 0. If you leave 0 out, throw it away. The non-zero real numbers, remember this symbol, this backslash symbol stands for set minus operation. So this set less the contents of this set. So R less 0 is the non-zero real numbers. So the non-zero reals, they form a group under multiplication. So there are lots of other groups involving various versions of addition or multiplication of numbers. There are lots of these around, involving the sets, involving versions of the sets, the integers, the rationals, the real numbers, the complex numbers, and lots of other number-like sets. And functions, say from the rationals to the rationals, or functions from the real numbers to the real numbers, or indeed the integers to the integers. So if you apply functions to these kind of sets, often there will be additive and multiplicative groups of those functions. You may have to exclude certain objects or bring certain objects in to make sure all the conditions are satisfied. Okay. So there's lots more examples of these to find, and we'll consider more in due course. But I wanted to show you another important example of a group which doesn't fit into that picture at all. It's not got anything to do with addition, not got anything to do with multiplication, or slightly different versions thereof. Addition of functions, multiplication of functions, etc. Yeah, it's quite a different object. So this is a quite different example. Now I'll introduce you to this, and we may continue to consider it tomorrow afternoon. So this has got a fancy name. It's called the dihedral group D3. And it's not that surprising that this is just one example from a large family of dihedral groups, where you can increase this index. And this is the group of symmetries, of a regular triangle. Under the operation of composition, composing functions. So here's our basic, there's a regular triangle. So a regular triangle means all the sides are the same length, all the interior angles are the same. So an equilateral triangle. Regular, for that you could mean equilateral. The sides are the same, the angles are the same. Now, by symmetries, the types of symmetries we mean, we'll think of it centered at the origin. So we'll think that this point there is just centered at some fixed point. The symmetries, the kind of things we allow as symmetries are rotations or reflections. Rotations around this central point, or reflections in various axes. So if you let R equal rotation, so these are all symmetries, these are all transformations that we do to the plane where the triangle lives. The triangle is living in the plane in R2, and these are functions of R2 to R2. Transformations of the plane that are going to leave the triangle unchanged. Well, they're going to move the individual bits of the triangle around, but there are certain transformations that you can do to the plane, and if you look at the before and after picture, you'll still see the same triangle sitting there. So what's the basic kind of rotation we could do? How much do we rotate the plane so that you're still looking at the same triangle, sitting in exactly the same place? Well, triangles are all about 3. So if you rotate by 2 pi over 3 radians, and just to pin it down, we'll specify a direction, and we tend to prefer anti-clockwise directions by some decision of the United Nations or something. So you rotate the thing by 1/3 of a full turn. You'll still be looking at the same triangle. Maybe not because my picture isn't perfect, but if you rotate it by a full turn, by 1/3 of a full turn, you're looking at that, which is still the same triangle. Or you could rotate it by 2/3 of a full turn, in which case you'd be looking at that, which, accepting my poor drawing skills, would still be the same triangle. Yeah, exactly the same triangle. Let's call that R1, or you could have R2, which is rotation by 2 of those. 4 pi over 3 radians. There's other transformations of the plane we can perform that will be symmetries of this triangle. There are various axes of reflectional symmetry. There's 3 for the regular triangle. going through each vertex and the center of the opposite side. Okay. If I take any one of these, let's take this one down here. If I reflect the plane in this axis, so reflection in an axis means you send every point in the plane, you draw a line through the axis at a right angle to the axis and go out the same distance the other side, and that's the image point. So this point up here gets reflected to a point out here. If you perform that to the whole plane, you'll still be looking at the same triangle there. To do that with the page, you've got to imagine reflecting the page in the thing like that. And my picture's without, but you might maybe see the same triangle looking at it. If you reflect the plane in that, you see, this vertex will exactly go to this vertex. And every point on this side will exactly go to its partner on the opposite side. And all the points on this line go to their partners on the points on that line. It's still the same triangle. Traditionally, we might use S for reflections, because S comes after R. And there's three of them. S2 might be called reflection in that line, and S3 will be reflection in that line. Of course, you don't have an S4 reflection in that line, because that's the same line as the one S4. So there's three reflections. So these are reflections, so reflections in the axes shown. There's one other thing you can do to the plane which leaves the triangle unchanged that we haven't listed. You can do nothing to it. You can leave the plane where it is, and that's the identity. It's a kind of rotation. You can rotate by 0 radians. Don't rotate at all, or you can rotate by 2 pi radians. Give it a full turn, or give it 29 full turns, whatever you want. Such a rotation leaves every point in the plane unchanged, sends every point to itself. So that will certainly be a symmetry of the triangle. Now, the reason that group theory comes in here is we understand that we can examine the symmetry properties of shapes, on the one hand, by listing out their symmetries. So you can name and describe each of the individual symmetries that the shape might have. But where group theory comes in, group theory examines the way these symmetries relate to each other. This is where the operation, so by this I mean we're considering the operation of composition. Because the symmetry of the object, we said, is some transformation of the plane that leaves the object unchanged as a whole. Still the same triangle. But therefore, according to that definition, if you compose two symmetries, if you perform one symmetry and then perform another one straight after it, in total, from beginning to end, the triangle will still be the same. Same triangle you're looking at, because both of the individual transformations leave it unchanged. So when you compose two symmetries, you must get another symmetry. But we've already listed all 6 of the symmetries of the triangle here. So that means that the operation of composition is a closed operation on this collection. If I pluck one of the rotations and one of the reflections and combine them using the operation of composition, I must get one of the other ones on the list. And studying that, understanding how all these symmetries relate to one another, gives you a much more detailed view on the symmetry properties of the triangle. And this is what group theory can allow you to get to. Okay? One way of viewing these, one way of seeing this relation is with what's called a Cayley table. Or sometimes called a multiplication table. Now, my experience from primary school, I don't know what yours was like, but I've seen one of my strongest memories from primary school is we were all made to cut up our cornflakes packets at home, bring in the blank pieces of cardboard, and we seem to spend hours writing the numbers 1 to 10 across the top, 1 to 10 down the bottom, and either putting in the entries in the table the sum of the two numbers or the product, the multiplication of the two numbers. Then we cover them in sellotape, then we keep them and we look these up as lookup tables for performing arithmetic. Probably got me where I am today. But this generalizes. So this operation, which seems like quite a primary school kind of thing to do, but higher level mathematicians are interested, will like doing this as well. So if you know what I'm talking about, if you've ever used or constructed one of those addition tables or multiplication tables, this is exactly what that is, except we're dealing with different kinds of objects, not numbers here. Now we're dealing with symmetries of the regular triangle. And the operation we're talking about is composition. So in the body of the table here, I'm going to put the product under this operation of the row and column headings. And then I'll allow that will allow me to see all the details or all the values of the operation in the group. But now we're dealing with composition. Composition is not commutative. And that means we need an agreement because, like in this place here, which is in row R2 and column S1, what am I going to put here? Am I going to put here R2 after S1? Or am I going to put in S1 after R2? Now, there's no correct answer to that. We just need to make an agreement and follow the convention if there are conventions. Like everybody drives on the left-hand side of the road. There's no reason for it except that it's an agreement everybody follows and things get along fine. So we need an agreement here, and the convention is for operation tables is that if you have a row X and column Y, the entry that goes here is X on the left and Y. Can't see what I'm drawing. X, the row heading on the left and the column heading on the right. That's the convention. And that agrees with the way that your matrix indices work. If you talk about an entry Aij of a matrix, you've got a matrix A. You've got a matrix A. The ijth entry is the entry that you find in row I and column J. So the convention for entries in a Cayley table is the same. Okay, the exercise, and we'll continue to examine this tomorrow afternoon, is every entry in the table here. So we've got 6 elements, and there's 36 entries to find. Every entry has to be one of those 6. Because when you compose 2 symmetries, by definition, you get another symmetry. We've already listed all 6 symmetries that there are. Things we can fill out straight away is the row and column against the identity element, because the identity transformation is by definition doing nothing. So when you compose that with anything else, the result is just whatever the anything else function did. Yeah? If I perform 2 actions, first I do something and then I do nothing, the result is the same as if I just did something. So composing with the identity doesn't change things. But things start to get a little bit more interesting when you compose non-identity things. What happens when you compose R1 with R1? When you do R1 squared, which symmetry is that? It must be a symmetry, because rotating by R1 and then rotating by R1 again leaves the triangle unchanged. R2, exactly. You rotate by a third of a turn, follow that by a rotation by another third of the turn, you get rotation by 2/3 of the turn. R2 after R1. What about this entry down here in this place? R2 after R1. It must be one of those 6. E, it's the identity, yeah? You rotate by, so what this means, R2 after R1. So you first rotate by a third of a turn, and then you rotate by 2/3 of a turn. What have you done in total? You've rotated by 3/3 of a turn, so 1 full turn, just the same as doing nothing. Same transformation. So it looks good so far. All of our entries come from the 6 elements, so we can continue that. Once we fill out this table, we'll have a kind of bird's eye view of what's going on in the group of elements together with the operation. Okay, we'll continue this discussion tomorrow afternoon, but in the meantime, you might try and complete this table. And we'll look at the results of that tomorrow afternoon, okay?